So hello, kids from Florida and from New York. So what we're going to do is we're going to go through sort of formally what the relationship is between linear motion, which we've been doing, x versus time, y versus time, z versus time. And we're going to relate that to rotational motion and see how they relate. And we've already, by doing the ants on the fan activity, we've already covered some of these introductory things, so I'll sort of spin through those quickly. We talked about what uniform motion is, uniform circular motion. We've talked about pretty much all of these things, and we're going to add on a couple topics later on. All right, uniform circular motion, we've already talked about. That's just moving around a circle at a constant rotational speed. So we can come up with some examples of this. Somebody give me an example of uniform circular motion that doesn't relate to things we've already talked about.
Orbit.
An orbit of what? What's orbiting?
Going around.
Hey, we've already used that. I already used this Earth going around the sun. That's a used example. I've already given you some pretty good examples, right? So we've already seen some examples at the end of the ants on a fan. Those were uniform circular motion. So, well, the example I'm going to use is we have a bike moving along at a constant speed. If the bike's moving along at a constant speed, what's the tire doing on the bike? It's rotating at a constant speed, all right? So that tire is going around in uniform circular motion. And just to give us a marker on that tire, what I did is I scotch taped an ant to the side of the tire, and so he could go for a ride. Well, we all know that ants don't need to be scotch taped. Do you think an ant could hold onto a tire at 20 miles per hour for 15 minutes? Have you ever seen a spider on your windshield on the outside hold on your car for like 20 minutes? I've done it from home up to Tingsboro, 32 miles, and a spider can hold on to the windshield the whole time.
Wait, what?
So I'm pretty sure an ant could hold on. So we've got an ant that's clinging to a tire for dear life as it moves along, and you can come up with other examples. Like we saw the Earth going around the sun is uniform circular motion, or very close to it at least. It's not quite circular; it's elliptical, but almost circular, and so on and so forth. The ants on the fan, and so on and so forth. Let's start without a few questions here. And you have these slides, so you guys can sort of work through these. So my first question, is the bike accelerating or not? So we're moving along. What's the bike doing? I'm moving at 20 miles per hour on a straight and level road. Is the bike accelerating or not? No. All right. No, we've got a constant velocity, right? So next question. How fast is the center axle of the bike moving with respect to the ground? By the way, respect to the ground, this gets into relative frames of reference, all right? And with respect to the ground means that you guys who are sitting on the ground as an audience, you're part of the ground, you're attached to the ground. That would be your perspective as this bike drove by. So if we were looking at this one point on the bike right here, where the axle connects, how would you describe that speed? Is that constant velocity, accelerating? What's it doing? That point looks like it's doing what? Moving, constant speed, which direction? To the left, it looks like, right? So yeah, that point on the bike or any other point on the frame or the person sitting on the bike would all be moving at a constant velocity. So that point is moving at a constant velocity of 20 miles per hour. I converted it into feet per second and meters per second. And I'm sure you guys know how to do that. All right? And these, by the way, should be answers on your worksheet that you have been working on. And so you guys can go back to your worksheet and work out answers on this. So, got some questions here. So how far does the bike move if the wheel turns once? And I'm going to use a BMX bike that has a 24-inch tire. What's 24 inches mean? What are they measuring when they're measuring 24-inch tire? It's the diameter. Sorry, Peter. It's the diameter. So if it turns once, we're actually talking about the diameter of the wheel. So what's the diameter in feet? 2 feet. So the radius is 1 foot. All right. So if we roll once, how far do we move? We move 1 circumference. right? If we roll once, we move one circumference. All right, so here's one roll. There's one revolution. And I'll just get my BMX tire here just so we can see it. I used to do this with like a 10-speed bike tire. Those are 26-inch tires. But this is just easier to work with these numbers because it turns out to be a radius of 1 foot. Don't leave your money around there. All right, so this is the size tire we're talking about, all right? So one revolution, take this off here, would be from, I'll take this, this red dot here. So the red dot gets down to right there. All right, that's one revolution. And the distance from there to there should be 6.28 feet. So you guys could measure that and double check me if you want it. All right. So our circumference actually relates to the distance this wheel is traveling. So if we think about circumferences, it helps make these ideas come together a little bit easier. All right, next question. Let's suppose the bike moves 10 feet, let's say. I want to know how many revolutions the ant makes. And we're going to use on my sample here, we can see the ant is this little sticker right here. So if my bike tire moves 10 feet down this table, I want to know how many revolutions does the ant make. How would you do that? How could you figure that out? Use logic here. Divide your distance, 10 feet, divide it by your circumference of your tire, all right, which is 6.28 feet. Because every 6.28 feet, we do one circumference. So divide by your circumference. So I'm taking my distance, and I'm going to treat this as slightly differently. I'm going to take, there's 10 feet that we're looking at, and I'm going to see how many revolutions we have per one circumference, all right? So I'm treating this as like a little conversion factor. So I'm saying I can take 10 feet, and there's one revolution per one circumference, and the circumference is in feet here, 6.28 feet. My feet cancel, and I'm dividing, just what Peter said to do, and Dalton was going to say, I'm pretty sure. And you get 1.59 revolutions. All right? Of course, you can convert this into what other units? Revolutions can be converted into cycles is a revolution. One cycle is one revolution, they're the same. That's 1.59 cycles. What else could you convert it into? Degrees, 360 degrees per revolution, and you convert it to radians, which is 2 pi radians per revolution. All right, I'm just going to do that real quick. So there's my answer in radians, and here's my answer in degrees. All those have the same meaning. That's your distance. That's your rotational distance. All right. You guys are used to talking about linear distances, 10 feet. Now we're talking about rotational distances, which is are revolutions, radians, or degrees. So they're angular measures, essentially. All right. So all those are measures of what we call, and the unit we use for angles, you guys know this from math, what unit do we use for angle? What variable do we use for angles? We use theta. All right. So that's what our theta represents. Our theta is our position variable for rotation. It tells you how far you've rotated, whereas x tells us how far we've moved in the x direction. Okay, so next question. If the ant starts at the 10 o'clock position, so let me line this up over here. By the way, I have some weights taped to this wheel. Does anybody know why? Is that about 10 o'clock position? Does anybody know how the weights taped on here? Stabilization, what's that mean? It has something to do with stabilization. Yeah, you're it's balancing the tire. I got to give Callum a bonus point. So if the ant starts at the 10 o'clock position, where did it stop? If we move 10 feet. So how could I figure on my clock face here where I stopped? And I'll put up here. Here's your clock face. If I have to move 10 feet, how do I figure that out? And we did this yesterday when we did ants on the fan. Suggestions? Quick? Well, I could use a little bit of conversions here, right? 360 degrees on a clock is 12 hours, so how many degrees per hour? Each hour is how many degrees? 30 degrees for each hour, right? So I can just use that. So if the bike, after 10 feet, I'm just going to use my ending units over there, that's 573 degrees. I can do, once again, a little bit of math here. I'm going to treat this like a conversion. I'll convert degrees into hours, because 1 hour equals 30 degrees. So I am treat this a little unit conversion here. And in do this, you get about 19 hours. It's a tad more than 19 hours. I rounded it to the nearest hour. I rounded down a tiny little bit. So the other thing, I could have looked at my answer up here. 1 revolution is how far around my circle here. Well, I got 1.59 revolutions, means I start at 10 o'clock. I go around all the way once, and then I come part the way around again, and up somewhere around 3 o'clock. If you look at this 1.5 revolutions, 1.59, if you look at 1 revolution is from 10 o'clock over to 10 o'clock, what's the 0.5 revolutions bring you over to? From 10 o'clock over to how far for 0.5 revolutions? What's half a revolution? Over to 4 o'clock, right? 6 hours over. And then I'm going 0.9 revolutions, so I have to figure out how far that went. But it turns out you're at around 3 o'clock. You're a bit beyond 3 o'clock. You're almost to 3. You're like between 2 and 3, very close to 3. This is a little bit more than 19 hours as the clock moves. All right. So that's what that answer is. All right. Next question. So I've got my ant. Let's say he starts at 10 o'clock again. And then let's say I ride for 15 minutes at 20 miles per hour. How many rotations, and where does the ant end up? How would I figure that out? What methods? There's a couple different ways you could solve this. How could you figure out how many rotations the ant has made and where he would be? So where he would be, we could use the same method as above, right, once we figure out the rotations. So how do you figure out how many rotations in 15 minutes? Suggestions? James? So if you could work out a velocity, if we have a linear velocity, and then do what? Yeah, so an angular velocity would be rotations per time, or radians per time, or degrees per time, then multiply by time, right? So if we get angular velocity in minutes, like rotations per minute, RPMs, then we can multiply by minutes, you get your answer, right? So if we can come up with a speed in rotations per minute, we could multiply by 15 minutes, and out would pop our answer, right? Because the minutes we cancel. So one way is to figure out your velocity, your angular velocity from this, and then multiply it by your time to cancel out your time units. What's another method?
Find distance that the wheel traveled.
Yeah, we can find, well, you can find the distance the bike traveled in 15 minutes, and then do what? Divide by the circumference to figure out how many rotations, right? Which is sort of what we did above. So I'll use that method, but both of those methods would work, right? This is actually what James told me. You can take speed times time, angular speed times time, to get yourself the distance, right? So here's my speed. I'm going to convert this maybe into, there's my distance. So I'm actually taking my linear speed. James wanted to do this angular method. Peter wanted to do it linear, so I'm going to start linear and work over to angular. So 20 miles per hour times a quarter of an hour, right? So I don't have to do too many conversions, and you get what? How many miles? 5. Take your hands off that calculator. And then what are you going to have to do? 5 miles. Circumference, which is 6.28 feet, so you better do what first? Better convert, all right? But the 5 miles is our x position, right? Or we can convert that into feet, right? So we just found our linear position in X, and we can do a little conversion here. So on our X-axis, we've traveled 5 times 5280 feet, which is a lot, right? So that's what, 25,000 plus another, 1,250 or so. So we're at about 26,500 or something, 26,400. So we've gone 26,400 feet along our X-axis. So we've figured out our linear position. How do we convert that to our rotational position? You said divide by your circumference, all right? So I'm going to convert my feet into revolutions, right? So 1 revolution is 1 circumference, and my circumference in feet here. So you do that little bit of math, and you get 4,201.69 revolutions. And then, so that's how many revolutions you did, all right? What do you think? What's the ant doing at that point? Is he still hanging on? Or is he too dizzy and he's fallen off by now? Now, the spider on my windshield, it didn't have to go around in circles over and over again. So the spider, it might be easier just to be either to deal with it 1D. I'm not sure, spinning around 4,201 times. That could be a little bit disconcerting, to say the least. So I don't know if an ant would stand for that long. Let's test it at home. Of course, we could figure out the clock position by using the same methodology, right? We could say, well, what's the quickest way to figure out your clock position from here? Yeah, we look at a natural clock and do what? What's the quickest way to tell where he is in terms of our 10 o'clock starting position? Let's say we start at 10 o'clock again. What would you do here? What math? What's simple math on this? 4,201.69 revolutions. What's important about that number? The 0.69 revolutions, right? So you'd convert the 4,201 ends you back up at 10 o'clock again. Take the remainder, the decimal portion of the remainder, right, and convert that piece into how many degrees or how many hours you've cranked through, and you can figure that out. So you can just take the 0.69 revolutions and see how many clock hours that turns into. All right, but what we've done is we've actually taken a linear motion here and we've converted it into an angular equivalent. All right, and that's our first big idea. So we're going to answer these 3 questions here. If a wheel rotates once in degrees radians, we're going to come up with a relationship between the 2. All right. So if a wheel rotates 1, it's like a wheel traveling along a road. Then we actually move 1 circumference in distance. That's what we determined. So 1 rotation equals 1 circumference in motion. If a wheel moves less than 1 rotation, how far does the bike move? Who knows this? What if we move, instead of 1 rotation, what have to move a piece of 1, theta radians or theta degrees, or a third of a rotation? What are you going to do? You're going to do what? Yeah, it's going to be a proportion. It's going to be proportional, all right? So you can compare theta to your entire rotation of 2 pi radians, right? And what that comes up with, we actually have something called an arc length here. And this is where the arc length formula comes into play here. You know this from trig. And this arc length formula is what? Anybody remember the arc length formula? Need the radius to do this? S equals r theta. It comes from those ratios. This arc length formula, I'll warn you right now, you can only use the arc length formula if you're using radians. All right, so this is really designed for radians use. So S equals r theta. So that if we actually move theta radians then, our arc that's been traversed here by our ant is S units long in meters, for example, and our bike has moved how far? It's moved that distance in meters. And so what we've just done is we've related a rotational motion to a linear motion directly. So we have x related to theta using the variable r. So it turns out x equals r theta. And that comes right from our arc length formula. Okay, and just as a reminder, in terms of angles and radians, what the relationships are, and rotations. So 1 rotation would be 1 circumference you move, half a rotation, half circumference, so on and so forth. All right. Now, if we're treating this then like it's the X situation and we draw a diagram with an X-axis, typically for an X-axis we say, all right, plus is this direction, either left or right. So we define plus. We need to do the same thing. We need to pick a 0, an initial position, and we need to pick which positive direction. Same thing for rotational variables. All right, so instead of X, we're going to use theta for our rotational variable in one dimension. Of course, is a rotating object, is that one-dimensional motion? Would you say that this spinning ant is moving in one dimension? It's one rotational dimension. You think about it. All right, we're defining a new one-dimensional construct here. It's rotational motion. All right, and we're going to be able to use the same type of 1D formulas you've seen before, but we're moving in a rotational dimension rather than a linear dimension. All right, and so we need to pick a direction, just like we did for x-axis. Which direction is our axis going? For rotation, that direction is whether we're clockwise or counterclockwise. And by the way, sometimes you will see me use some abbreviations. CW clockwise, CCW is counterclockwise. In math class, why is counterclockwise positive? Give me an example in math class why that's true. Our unit circle, right? Or our quadrants. Quadrant 1, 2, 3, 4, that's counterclockwise. We start at 0 degrees on our positive x-axis, we're counterclockwise. So if we use positive to be counterclockwise, that's sort of aligning things with what the mathematical way of seeing things are. Does that mean we couldn't define positive as clockwise? No, we can draw our axes whichever way we want them. We can tilt them and put the positives on the other side. We can do that, all right? Same thing here. Standard, I would say, is positive as counterclockwise, but it doesn't mean you couldn't define positive as clockwise as well. Either way works. Okay, so we've got a counterclockwise. So on this one, we use counterclockwise. 0 degrees in math class, you would use that as a positive x-axis. But once again, I could define 0 anywhere I want to. I could say 10 o'clock on the clock is my initial position, is my 0 position, right? So that's just an arbitrary point you're picking as your initial position. So we've related. So far, we've related position to our linear position to angular position by using r x equals r theta. Or if we solve for theta, theta equals x over r. All right?
Excuse the interruption. All swimmers will be dismissed at this time.
I do not excuse that interruption. So I'm going to jump ahead here, and we're going to look directly at velocity. We're going to go through another argument of how to look at velocity in a second here. But I'm going to go back to my definition of average velocity. Velocity equals delta x over delta t. All right? And I'm just going to work out another way to look at angular velocity using this definition of linear velocity. So if I just take my value of x equals r theta, so I'm going to replace in my equation, I'll replace delta x, and I'll replace that x with r theta. Here's what I get. So here's my average velocity equation. Average velocity is change in position over change in time, but I'm going to replace my x with r times theta. All right, so this is a change in r times theta. Now, is r changing on this? Does my radius of my wheel change? So that's a constant. I can factor that constant out front, all right? And what I get is r times delta theta over delta t. Well, what's your change in angular position with respect to time? What's that called? That's called your what? It's not frequency. It's related to frequency. Radians per second. Rotations per minute. Degrees per second. I'm dividing all those variables, giving you all the variables, the units that would come up. That's angular velocity. What letter of the alphabet would we use for that? Omega, a Greek letter that looks like a W, a curly W. So it turns out that we have our linear velocity is related to angular velocity in a very similar sense that our linear position was related to angular position. We have x equals r theta, and we have Vx equals r omega. So if I double the radius, what happens to my angular velocity? Doubles. If I halve my radius, what happens to my change in my position? It halves, all right? So we've got a proportional relationship between position and velocity, linear position and angular position, and the same proportional relationship between linear velocity and angular velocity. And we saw this on the ants on a fan worksheet. We actually calculated positions and we calculated velocities. And we saw that the only thing that changed, our angular speeds didn't change as you moved out in your radius, but your distances you traveled changed as you doubled your distances, and your tangential speeds, and somehow tangential speeds are going to be related to my linear speeds here. We're going to see that next. If you double your radius, your linear position, your linear velocity doubles as well. All right, so we've got a little summary table here to fill out. So what we've got is we've got a circle. We've got an ant sitting on the circle at radius r. We're going to define positive to be counterclockwise. And I don't know, let's see if I come up here. There's also another way to define this motion in terms of using something called a right-hand rule. And if we don't do it now, it will come up later. But I'll just show you right now. Right-hand rule, I would take the axle of this bicycle and I'd grab the axle such that my fingers curl around the axle in the same direction as my rotation. If I were to do that, which way is my hand going to point out? Point into the board or out of the board? Out of the board. Thumb's pointing out, right? Got to use the right hand. All right. So using the right hand rule, if I grab the axle in the same direction of rotation, my fingers are curling. This direction would also be known as out of the board. All right. Into the board would be the other direction. And that's using what we call the right-hand rule. All right, and you're going to see that's a very common way to describe what direction rotations are, rather than saying clockwise or counterclockwise. Okay. So our first goal here was to relate our change in angular position to the change in linear position. And what did we do? We used S equals R theta in essence to do that. We started with one circumference, with S equals a full circumference, all right? And then we changed it into something a little more accurate. So we came up with this. So we have our position variable in linear motion is x, or delta x, if we're talking about displacement. And remember, that can be a vector. And I give you some typical units. We use meters or feet, whatever. On the right side, we have our rotational motion variables. And instead of x, we use theta. So x and theta are our positions, our linear position or our angular position. Delta x or delta theta is our displacement, our linear displacement or our rotational displacement. Typical units for our rotational motion are radians, degrees, rotations. And remember, rotations and revolutions mean the same thing. And there are other ways of measuring rotation as well. Well, these are just a few. But those are the most common, certainly. All right, and how do you relate the two sides? Well, it's through x equals r theta, or delta x equals r delta theta. Good? All right. So before I asked you a couple questions, I asked you one question about if you were to look at the axle of the bike as this bike were moving along at 20 miles per hour, what motion does the bike seem to be going on? So this point right here would be moving how? To the right at a constant speed, all right? Now we're going to change our perspective a little bit and look at not the bike moving, so the bike is moving straight across, but what about the ant? And it depends on your point of, your frame of reference, where you're sitting to watch this, all right? So we're going to look at some different frames of reference to do this, all right? So the first, there's you guys. Sitting and watching this and having obviously a great time in physics doing this. What kid wouldn't have a good time doing this? And so as your first frame of reference is a side observer sitting on the ground watching this go by, all right? So from your point of view, you in the audience, like this little kid, Actually, this little kid's going to see something slightly different than you guys, right? Suppose you observe the ant's motion if you are, and I give a few different situations, sitting on a stool watching the bike ride by. Now, you guys are sitting out the stool in the audience right now. This kid's sitting out the stool as well, but he's going to see something slightly different from you. So what are you going to see? It will move, and this is the path of the bike. The bike is moving from left to right in a straight line at a constant speed. All right, so you see that. What does the kid see? He sees it. He's on the opposite side, so he sees it. You saw it left to right. He's going to see it from right to left. All right, but otherwise very similar. All right. Next, let's say that instead of you guys sitting here, you guys are all riding bikes as well alongside this bike. So what does a bike appear? How does the bike appear to be moving in that case? Yeah, the bike appears to be stationary, right? And the little kid, on the other hand, appears to be going by. So the ground appears to be moving by you, but the bike appears to be still, all right? And we've done this before. We saw this with what example? We did an example before. Somewhere.
I don't know, rain.
The raindrop.
Raindrop. Yeah.
Now, let's say you have, let's suppose you are sitting, you shrink yourself down, and I think there's a movie coming out right now where somebody's getting shrunk down. You shrink yourself down and put yourself on the spoke, but very close to the axle. So what motion does the bike appear to have in that instance? Slight? What do you mean slight? The bike looked like it was doing that. Now do that for 15 minutes. And then you can think of other situations as well. But motion is relative. You got to think about the frame of reference you're setting up for motion. Okay? So, my question is, what about the ant's path from each frame of reference? What does the ant appear to be doing? All right? If you guys are sitting out there, remember we have the ant on the edge of the tire rolling around. What does the ant look like from your side view over there, or if you're riding on the bike, or if you're sitting on the hub of the bike? That's what the ant's path looks like. True? Isn't that interesting? How fast is the ant moving? Now, this is a frame of reference from you watching the bike go by, right? The ant moves, it starts down here, let's say. As the bike rolls, the bike tire rolls, you can see the bike tire rolling. The ant moves up, then it comes down, then it goes up, then it goes down. Right? And so it looks like it's tracing out that path in time. And you could actually do this on Logger Pro. You could actually ride a bike by with a sticker on it and track it out, and you'd see that red path being tracked out. The hub of the bike looks like it's going straight across the page at a nice constant pace. But an object that's on the edge of the bike has that path. How fast is that moving? That ant. Constant velocity? Well, let me ask you, is the ant moving at uniform circular motion at a constant rotational speed? All right. Is it moving at a constant speed? And that's constant speed relative to what? Relative to what position? If you're watching the ant on a fan looking right below and watching it, that would be constant speed for the ant. Is the ant moving at constant speed from somebody sitting on the side like you guys are watching go by? It's not constant speed? Dalton's shaking his head, no way. Is it going faster in some places, slower in some places? What's the maximum speed and minimum speed? What's the minimum speed the ant's moving? When it's at the bottom, and how fast is it moving then? Zero. It's actually moving at zero. If you think about it, that's where the bike tire is touching the ground, and you're on the ground, and is the ground moving with respect to you? No. So when that ant is touching the ground, it has to have a zero velocity with respect to you guys, right? And so its velocity, when it touches that ground, and the ground is not moving relative to you, it has to have a zero velocity. It's one way to think about that. And if you watch it closely, you can sort of see at that point it sort of comes down, stops for a moment in time, It's an instantaneous thing, right? And then it speeds up again. Where's it going the fastest? It's going the fastest when it's in which position? At the very top here. It's going the fastest if you watch it. All right. The question is, what speed? So we know it's going 0 at the bottom. How about in the middle? If an object in the middle is going what speed? 20 miles per hour. At the bottom, when it touches 0, it's going 0. All right. So Dalton gets a bonus point. Peter gave you a bonus point. Good job. So erase one of yours, give it to no Dalton. No, that's worth a bonus point, definitely. Yeah. So if you think somebody earns a bonus point, yeah, you can. Well, I'm not. No, if I let you guys do this, I'd have you guys giving yourself bonus points all the time. But yeah, thank you for pointing that out. He deserves a bonus point for that. Okay. So here's what did I just draw here? This is a motion diagram, all right, just so you can sort of see what's happening here, where you can see in red the position of the ant over time in equal times versus the position of the bike would be these black dots going along in time. All right. So the bike is going at a linear constant velocity, and the ant is going through some crazy path. This path is actually called a cycloid. All right, so it's an interesting mathematical construct. I have a little bit of information. We've already answered this question. What's the ant's velocity? The highest, lowest. When's it at 20 miles per hour? That's an interesting question. When is the ant's speed, if it's zeroed out at the bottom and some high speed up at top, where's it going to be 20 miles per hour? Is the top 20 miles per hour, you think? On the green line, you think? When it's parallel to the green line, moving parallel to the green line would be at the top.
Oh, right.
But it could be going 20 miles per hour up here, maybe. Where's it going 20 miles per hour? That's a good question. Let's figure that out. A little bit about cycloid mathematics. Somebody take a picture of this and post it on our Wikiforce real quick, on our Facebook page, just so people will have this.
I don't have a good phone, Mike. Should I get a glaze? Can I get...
Maybe when you guys get it from the side, so there's less glare. And post that online. Let me move this out of the way. Just in case anybody wants to see the math behind it. This is pretty interesting math. This is, I just cut and paste this off of, there's my source up there. And this is an example of, we've X is a function of time, Y is a function of time. You could actually toss this in your calculator. I showed my period 4 class, by the way, how to use the parametric mode on their calculators. If you look under mode on your calculators and you see you have function mode that you're on right now, you can actually shift that over. It's right under your radians and degree setting. You can shift it over to parametric mode. And when you go into your equations, to enter your equations in y equals, you'll see instead of y equals a function of x, you can have x as a function of time and y as a function of time pop up. So you can actually map these things out and play with them a little bit. And how do they go from here into this equation down below? X is a function of y. You should know how to do that. How do you go from this parametric form up top down to this form right here? Substitution of what, Andrew? Yeah, solve for t and replace the t. Get rid of the t. That's what we did. I think I owe Andrew a bonus point for seeing that. That's good. Yeah, so I could solve this equation for t, one of these two equations for t, substitute in the other equation, and that's where this equation comes from. All right. I've got x as a function of y. So that's your Cartesian version of the equation. Oh, hold on. Did you used to read that in my in the writing? If you're eliminating t in both equations, I guess it's right up there. He didn't read it. He says, so we'll give him that. So that just maps out. That's just an interesting little side fact, not so important for what we want to do overall. However, from a calculus standpoint, if I wanted to figure out what my velocity is at any point in time, what could I do? And for you AP Calc folks, I want you to do this. How do I find the velocity of the object if given this position equation. And x is a function of time, y is a function of time. Just like equation 5 and 6, sort of, but this is not for 1D motion anymore, right? Take the derivatives, dx dt, dy dt, and that'll get us your x velocity and y velocity, right? And how do you get your total velocity once you get that? If I have an x velocity and y velocity, how do I get my total velocity? Those are my x and y components, so I can square both of them, add them together, take the square root to get my magnitude. So I want to find out, please, using this, so this is a special homework for the AP, my honors kids can do it if they would like to for extra credit. Take the derivative of the two values, add them together, we'll put them back together into one single velocity, and then see at what times it's at 20 miles per hour. But you're going to have to figure out what your, this is a little bit tricky because you got to figure out what your A's mean in here, and you're missing a little bit into your time. So this will be extra credit, I guess, because it takes a little bit of thinking. This is a generic equation, and we have to figure out how to fit it into this equation for our 20-mile-per-hour bike. All right. So if you can figure that out, and I'll give you a hint right now. You've got to replace. There's something in front of the T. They have a 1 in front of the T right here, and you need to replace it with something else. So I'll make this a bonus for everybody. All right. But that's what we could do. If we had the correct variables to match up with the other function on the other page, we could take the derivative of each. It'll give us x velocity, y velocity. Then we can put them together using vector rules, and then we can actually see where it is 20 miles per hour. Is one way to figure out where it's at 20 miles per hour. All right. So let's take a look at this scenario, and let's see at a variety of different locations what the ant's relative speed would be, looking at having you guys sit out on the ground a distance away and watch him drive by, the bike drive by at 20 miles per hour. So you tell me. Here you guys are sitting in the audience. Looks just like Peter when he was a little kid. Did they put a bowl on your hair when they cut that, Peter?
Oh, yeah. I actually dyed my hair black now.
So. You dye your hair black now. So
It looks like it should be.
So if the ant is on the axle, what do you think? And we're trying to figure out the speed of the ant, all right? You can get the direction as well to get a velocity. What's the speed of the ant riding on the axle if the boy's sitting there? It's going to be 20 miles per hour to the right, all right? And so this is the first one where we have the boy sitting here, the ant's on the axle, it's moving by from left to right here, right to left from the boy's perspective. And so this one's going to be, this is the easy one, right? So the ant's just sitting right along the middle of that bike tire, 20 miles per hour. Now, what happens if, when the ant is on the edge of the tire now, and he's at the 6 o'clock position, he's actually, the ant at that instant time is on the ground. So what's his instantaneous velocity at that point? It's 0 because it's touching the ground is not moving, and so it must not be moving either. So at point B, and you notice I have a no-slip situation. If our bike was skidding along the ground, he could have a velocity, a forward velocity if he were sliding. Okay? And so at point B, he's going at 0 miles per hour. At the 12 o'clock position, what do you think's happening?
40.
And this is our 40. All right. Do you have any justification for 40? This is Jock was saying 40.
The bottom 0, then you go halfway up to 20.
So you're saying some sort of proportion happening here. Why not? Better than nothing for a guess, right? But it's probably not 20. If 0 here, 20 there.
I don't think it's 20.
All right. Well, let's see. Let's see what we got here. Here's how I'm going to explain this. Let's say I were to take, I'm going to take a meter stick here, and here's my ant on the ground. If I were to put this meter stick on this tire, all right. So here's my instant time where that's happening. This handle's good. I can adjust that. Here, hold that for me. Okay, so here we are at this point in time. All right, this bike's rolling that way, right? Now, here's what we're going to do. So I've got points. B is on the bottom here of the tire, all right, on the bottom of the tree. We're gonna just tape this right to the wheel, just at this point in time. And we've got the axle, the hub, is right here in the center, 1 foot up, and 1 foot up there, another foot up is our ant. And what I'm going to do is I'm going to say, if we go a tiny bit in time forward, what's going to happen? What's going to happen if I move time forward 1 little instant in time? An instant in time. What just happened? I'll do it again. Ready? What happened to the ant? I'm down here. Right, here's an instant in time. Didn't really move in an instant time. What about the middle of the bike? It moved a little bit. What about up here? What about way up here? What if I had a mile-high meter stick? You'd move a huge distance, right? So something's happening similar to what you said, right? The higher you go along the stick, the faster that object is moving. And that's how I'm gonna visualize this. So after a small change of time, the tree tips a little bit, all right? And at the bottom, your point B doesn't appear to move at all. Your point A, we already know point A is moving 20 miles per hour, and that's through a length here of 1 foot. So 1 foot away, I'm rotating this way, and it looks like I'm rotating almost, right?
Good afternoon, things
So,
please listen up.
So it looks like
Athletic announcements today. Boys
I'm rotating through a tiny little arc here.
Green will tech tonight at 7 o'clock. GD starts at 5:30. Our swim team.
So that's my S. S equals arc theta. So if I go way up here then, I've got to double the radius, and I'm going to move through a much larger arc. If I double the radius, my arc length is going to be doubled. And if I take that distance over the time, delta t, what do I get? I get velocity. If I take this distance divided time, I get velocity. Well, we know this velocity is 20 miles per hour. We know at double the distance, we rotated twice as much on our arc length, so our velocity has to be double. So do we owe Jacqua a bonus point? I think so. Oh, yeah, that's right. And he needs a bonus point, so. So that's our argument for that, all right? And so at the top, our velocity should be 40 miles per hour. All right, so that's good intuition there. All right? And you can see this argument, you can go back online and watch that, all right? What about on a spoke halfway between? If we're at point D here, what would happen then? Using the same argument, we'd move 1.5 arc lengths compared to this arc length, and we'd be at 30 miles per hour. And for that instantaneous speed. And really what we're getting out of here is our tangential velocities, aren't we? We're looking at the tangential velocities at the end. Relative to your frame of reference, okay? And we sort of saw that. Dalton saw that on our, a couple people saw that on our cycloid. It was going very fast at the top, and down the bottom it was going 0. So this relates right back to our cycloid. How about at 3 o'clock and at 9 o'clock? I don't know. Now you got to remember, because if we're moving to the right, it looks, if the bike tire where you're sitting here spinning, it looks like you're going down, but you're also moving to the right. So we've got to take that into account. So this is a little bit more complicated. So I'm going to let you guys think about that. All right. So what I want you to do for homework, there's a few slides here. And sorry, these slides might be numbered slightly different years. You're going to answer this slide through the end. There's another section coming up here. And there's a couple homeworks. It'll go through page, let me just take a look here real quick. That says the homeworks on it, all right? So yeah, I want you to work those through slide number, On yours, it's slide number 28. All right. So you're going to work through those slides. All right. This will be posted up as a video if you wanted to go back to our lecture today. I don't know. It's not going to be edited at all, so no Oscar-winning video this time around.
Well, soon,
But every producer has a bad film once in a while.
there'll be